kind of gives me a good idea of what the other one's going to do. Because basically, I should get the exact same series. Right? It seems to be almost always the case, if not always the case. You get the same series, but one alternates and one doesn't. Right? That really should be what's happening if you do this, correctly. Right? So if I put in 4. I'm going to skip a step quick, right? 4 to the end and 4 to the end will cancel. Everybody okay with that?
Yeah.
N over
All right.
n squared.
So I get n over n squared plus 1, right? All right. And so I've got to figure out what does that series do, right? And what's that series going to do? Won't approach a half. Diverge, why?
Because when you simplify it, the p-value is less than or equal to 1.
How do you mean when you simplify it?
Because you can factor out an n from the and then you can cancel the n on top. So then you can cancel it with the n on top. So you're left with 1 over n plus 1 over n.
Okay. So if you rewrote this, you're looking at this as 1 over n plus 1 over n?
Yeah.
Okay. And then what?
And then, what is that called? The p value is...
Because it's not in that form. So, I bet you're on the right track, but I need to use, what? No, because that term is going to go to 0, right? Which tells me nothing, right? But you're talking like, you think this is like what series?
Oh, 1 over n.
Okay, so therefore you need to use a comparison test, right? I need to compare this to, right? So you're talking your good stuff about, hey, this thing's going to act and should do the same thing as 1 over n does. Yeah. You need to then compare it to 1 over n, right? Either using direct comparison test or the limit comparison test. And again, I think the easiest one is to simply use limit comparison test, right? The idea we're going to look at here is we're going to do a limit comparison test, right? So we're going to compare it to 1 over n. So we get n over n squared plus 1 over 1 over n, and find the limit as n goes to infinity. Okay? So again, these polynomial over polynomials, right, for large n's, this is basically n over n squared. So it's basically 1 over n. Right? This n's going to kick to the numerator. So you're going to get n squared over n squared plus 1, which if I factor an n squared out, right, I'm going to get 1, right? Which means the two series must do the same thing, right? Okay, and since 1 over n diverges, what do we call that series? Harmonic, right? That's a harmonic series, right? The harmonic series diverges, right? Diverges, harmonic, p equals 1, either one of those two. I would just say diverges, harmonic. Okay. Then n over n squared plus 1 diverges, right? By a limit comparison test. So 4, don't change it, right? Non-inclusive.
Mm-hmm.
Yep.
So in the fairness, we don't have to verify how we know that it diverges. We can just say that we know that 1 over n diverges.
Well, I did. I said it's a harmonic.
Yeah, we don't have to show any work for why 1 over n diverges, right?
Well, you got to tell why. So I told why I know that is because it's harmonic, and I know the harmonic series diverges. That's a known fact. Or you could say because p equals 1. Right, it's a p series. Yeah, but this one's got a special name, and the harmonic series diverges. That's just a known mathematical concept. So I am telling them how I know. All right. So at the other end point, I'm going to have this series except I'm going to have a -1 to the n on it, right? You put a -4, right? So -4 to the n is -1 to the n, 4 to the n, 4 to the n's cancel, so I'm left with the alternating. Right? Well, I already tested for absolute convergence and found that it didn't work, right? Yes? Okay, now I've got to see, does it converge conditionally, right? Okay, so now I've got to look at, the big question is, do these terms go to 0? Do the terms get smaller, right? And are they always positive? Well, n over n squared plus 1, those are always positive values, right, for n greater than or equal to 1 or 0, right? 0, I guess it's 0, but from there on you're good, right? Do they go to 0? Sure, the limit as n goes to infinity, right? I'm going to have n over n squared, right? So the terms go to 0, right? And then the last one is really kind of showing that the terms get smaller, right? Well, as n gets larger, n squared plus 1 gets bigger, right? So the fraction gets smaller. I mean, you can look at, you know, as n plus 1, and we have a little bit higher expectations, so I've got to show that this is always less than or equal to n over, you know, n squared plus 1. That's sort of my, you know, goal. So I'd have to show, right, that n plus 1, you know, over n squared plus 2n plus 2 minus n over n squared plus 1 is less than 0 or something, you know, I mean, something along those lines. And you could get some common denominators, you could do some math here, you know, put these things together, and if you follow through on the math, you'd find that this is negative, which means it's less than 0. I'm not going to keep going with the math on it. I don't think the big expectation in this course is to do that. You're more just kind of, you can think it out and go, n squared, that's going to keep getting bigger and bigger, right, as n gets bigger, right? So my fraction is going to get, you know, smaller and smaller, you know, as you go through. So, and n squared is going to dominate the function.
Can you just leave the factor on n though?
Yeah, I mean, and then look at this as 1 over n plus 1 over n.
Yeah.
Right, you could rewrite it that way. Right, I mean, does that help maybe a little bit in your process? Still got to kind of go through the same thing and figure that out a little bit. So, again, I don't think it's a necessary thing for this course of taking it that far. You're just kind of looking at it. So, at -4, what does the series do? Converges conditionally, right? Which means it converges, right? I want to make sure we understand that this series, right? This series, when I put this series right here, that series converges, right? That's going to sum to some finite number, right? Right? But this series is only conditionally convergent because it only converges because it's alternating, right? I mean, that's sort of the idea with it. Okay, so when you're saying something conditionally converges, you're still saying that series converges, but you're saying only that series converges, right? It doesn't tell me about other series, right? It doesn't tell me about that series, right? Because that series actually diverge, right? So that conditionally convergence is a pretty, you know, tiny series, right? It doesn't tell you a whole lot. It just tells you that that one single series converges. Where absolute convergence tells you that any series that basically has these same numbers, positive, negative, right, converges. So it's a much more powerful, you know, statement from that regards. All right. So that's our big idea. So we've kind of hit on all the stuff that we need to know. We'll do a bunch more practice problems over the next couple of days. My thought is probably actually have the test Friday. We could do it Thursday. We'll really see how tomorrow goes. But I think there's a lot in here that, you know, 2 or 3 days of practicing stuff probably isn't the worst thing. Even though it might seem like, oh, that's a lot. And we'll see. I mean, if we're cruising through tomorrow and feel, you know, really good by the end of the day, Wednesday, where everybody's like, yeah, let's just do it, then we can do it. But we'll see how you kind of right? If we're
Yeah.